He's a software engineer at IBM Zurich. He holds a master's degree in computer science from ETH Zurich. Jonas's research interests are in virtualized distributed systems and data centers, especially in the state-of-art network and storage technologies. Jonas holds multiple patents and research publications at top-tier conferences in the area. He's also an active member of open source community and contributes to tools like Apache Trail, DPDK, SPDK. So I'm very excited to invite Jonas to our day 3 of the conference, and I'm here to listen what he has to say about software-defined storage using the SmartNICs technology. So Jonas, the stage is to you.
Thanks, Divya, for the introduction. So yeah, this talk is about how to efficiently provide software-defined storage using SmartNICs. And let's start up with what the motivation was why we wanted to look into this. So SmartNICs have been the state-of-the-art solution to provide network and storage virtualization in cloud environments. What I mean by that is all the big cloud providers, being AWS, Microsoft with the Azure platform, they all use SmartNICs to do network and storage virtualization. These are custom designed SmartNICs like AWS Nitro or Azure SmartNIC, and they use them to provide isolation, security, and increased performance while being more cost efficient and consuming less energy. Now, what we've seen recently, that there's a new set of commodity SmartNICs now available for the wider public, that being NVIDIA Bluefield, Broadcom, Stingray, or Pensando as one of the startups working on SmartNICs. And they include a broad set of storage and network virtualization options. You have overlay networks, embedded switches, NVMe emulation, encryption, and so on. Now, you might think some of these are very familiar, and like your typical 100 gigs NIC also has these. So I will tell you in a second what I think personally is the differentiating factor between like a standard NIC with offloading capabilities and a SmartNIC. And we basically wanted to look at, can we use one of these commodity SmartNICs to provide transparent storage virtualization, specifically with CEPH as a storage backend? Okay, so what I have here is at least my personal view of how the landscape looks at the moment, and it's just a momentarily snapshot, right? The order that might change. So what I have from left to right is I order them by what I call programmability. And what I mean by that is data path programmability. And I think it will become clearer in the talk later in why I make this distinction. So on the very left, basically, this is what you all should be familiar with, is your typical NICs that we have today with various offloading capabilities. We have RDMA, network function, TCP offloading, and so on. And then for me, this is where the kind of differentiating factor is. From there on, all the ones to the right are basically NICs that are self-sustained. So at least theoretically, you could provide power to them without them being connected to the host, and they could boot up their own internal system and run by themselves, right? First one, we have a NIC basically like we saw on the very left, with an ARM on the side. Then we have a bit more powerful setup, maybe a bigger CPU or even a GPU. Then we have specific ASICs for network processing engines, like a P4 programmable NIC that would be, for instance, Pensando. And on the very right, we have the FPGA solutions where you basically can do everything that you can imagine. Okay, let's look at the specific use case for us was storage virtualization. And the goal here was to provide transparent software-defined block storage for bare metal and virtual machine in a cloud environment. And if you look at the block diagram, basically your customer in a cloud environment would sit in the red box, right? So he should not be able to escape this red box, and he should not be exposed to anything that's outside of this red box. So in a virtualized environment, this is a virtual machine. In a bare metal environment, it's your host essentially. And then on the very right, we have a software-defined storage, could be Ceph, could be anything you can think of. And we have some control plane that manages the whole thing. And essentially, we came up with a list of requirements, what we wanted the system to look like, or this proof of concept. So we wanted to have transparent block device emulation to the host or the VM. And that means we wanted it in a way that you in the VM can run your normal Linux or Windows or whatever you run without having a special storage driver. So, for instance, could be an NVMe block device to the host. And then for the VM specifically, we wanted that the hypervisor is not part of the data path, mainly because of performance, right? So essentially some pass-through option to your virtual machine. And then we wanted to have a control plane that allows you to add and remove block devices to the host. And obviously this should be outside of the red box somewhere that the customer doesn't have access to that. And the last one, you could imagine many things here. One we picked was data encryption with key management should also be at the client side. We want to essentially enable end-to-end data encryption on the client side. Could also be compression or some other features, but this is the one we kind of picked here as a requirement. So the question is this a perfect fit for SmartNICs? And I believe it is. So this is basically the same picture like before, just that I put them here side to side. I have a bare metal machine again and the VM. And now we have a SmartNIC component underneath instead of the NIC in the NIC box, right? And if we go from top to bottom, we have a block device emulation. As I said before, it could be exposing an NVMe PCI device to the host, for instance. Then we have an encryption component on a data path. Then we have a storage client that talks to your storage-defined software-defined block storage, and we have some control layer in a SmartNIC and outside that ties this all together. Okay, so what we had available was this kind of on the scale of we have a NIC plus ARM setup, and how this typically would look like is you have an ARM core, some ARM cores with some DRAMs to it, and then you have a PCI switch which connects internally to the 100 gigabit NIC here in this example, and then you have a few offloading engines on the NIC ASIC that you can basically control from the ARM side. Right. So now comes a point where, okay, how do you do this block device emulation, talking to a storage a box on one side, and on the other side, you want to have the block emulation to the host as a PCI device. And you essentially, when you are in, I call this mode fully offloaded block device emulation, is you need to have the particular offloading engine available on the NIC to be able to do this. Essentially, we have some control paths that sets this up. In this example here, for instance, the NIC would be capable of talking NVMe over fabrics initiator to some target outside of the host, right? And then we have a block device emulation that directly feeds into this and provides a PCI NVMe device to the host. Everything, basic data path, stays in the ASIC part, in the NIC part of the ASIC, fully offloaded. If you have a storage protocol that's not supported by the NIC ASIC, then you might have in this NIC plus ARM scenario, it might look something like this, right? You have a storage system, in our case, like CEPH outside, basically talk to the NIC, and you have a storage client then on the ARM side running, like for instance with TCP protocol. And then you have some connection from the ARM back to the block device emulation, and then you provide the PCI NVMe device to the host. These are the kind of two scenarios we looked at. Okay, then let's quickly talk about CEPH. So CEPH is an open source, massively scalable software-defined storage system. It builds on a distributed object store. The object store and the protocol is called RADOS, and it offers a variety of different APIs. There's an object API, there's a block API, and a file API. We concentrate here now on the block API. This is called RADOS block device, RBD. And on the right side, you see that essentially on the bottom, you have the storage servers. And the storage servers essentially consists out of monitoring and monitoring daemons. You typically run multiple to be fault tolerant. And then you have the OSD daemons that provide basically the actual storage. So behind an OSD daemon, there's typically a single drive. It could be a spinning disk, or it could be an SSD that provides the storage to the client. And then on the client side, you typically have something like, for RBD, it would be librd, or KRBD, that would be the kernel implementation to provide you a block interface. And everything between the storage servers and the clients is talking this RADOS protocol. Okay, let's look at how this looks in the real world. And essentially what we tested is, we tested 3 different configurations. So on the very left side, we have our baseline configuration. It doesn't include any SmartNIC. It's just a standard 100 gigabit Ethernet NIC. I'll show you in a second what the exact setup is. Essentially, we have CEPH. It talks RADOS to an x86 host. And we have FIO in user space with librd running the CEPH client directly talking to CEPH. Then in the middle, we have what we call a gateway NVMe over Fabrics RDMA. And what this essentially does from bottom up is, we have CEPH again talks RADOS to an intermediate host, which runs SBDK, which basically translates from the RADOS protocol to NVMe over Fabrics by exposing an NVMe over Fabrics target. You don't need to run this necessarily on an extra host. You could just run this on one of the CEPH servers. But I choose to draw it this way. It makes it clearer, I think. And then in this scenario, we have a SmartNIC, and now in this scenario, we run the SmartNIC in fully offloaded mode, like I showed you before. This ASIC supports NVMe over Fabric RDMA directly, so the ASIC connects to the SPDK running here on the gateway, and on the other side, towards the host, exposes a PCI NVMe block device, which runs basically here on the host, the normal Linux NVMe block device driver. And on the user space, again, we have FIO, but instead of using the CEPH library here, we just use libaio to do the benchmarks against the block device and the kernel. Now on the very right side, we have the solution that basically moves the gateway into the ARM of the SmartNIC. So now we talk RADOS directly to the SmartNIC, and we have SPDK running in the SmartNIC, translating between RADOS and NVMe over Fabrics, and the ASIC connecting to it, and again providing a NVMe block device to the host with FIO on top. This is essentially the 3 configurations we ran. Okay, let's talk about what the setup looks like. So for the CEPH server and clients, the clients have the SmartNIC, the server just have a ConnectX 500 gigabit card in it. And these are normal x86 servers with a bunch of memory, Ubuntu 2004. And we just gathered some baseline TCP performance numbers. This is not like specifically optimized. It's just to get like a feeling of where you can see the performance looks like. On the right side, we have we use NVIDIA Bluefield 2 as a SmartNIC. So all the x86 clients have the SmartNIC in them, and they have 8 ARM cores, is A72. And the version we are using is clocked at 2 gigahertz, 16 gigs of RAM, and it's a dual port 100 gigabit Ethernet interface. And essentially from all the numbers here, I think these two numbers are the one we should look at, the throughput numbers. So you can see that on an x86 machine, obviously you have enough horsepower. With enough threads, you can easily drive the 100 gigabit Ethernet with TCP. Whereas here on the ARM side, even using all the cores, we are only able to push around half of the throughput of the ARM when it comes to TCP. And since, of course, our CEPH protocol talks TCP, that means even if we had a zero overhead libRBD implementation, the 52 gigabits, at least throughput-wise, would be the best we could get out of the ARM side of the Bluetooth. Okay, then let's talk quickly about the CEPH setup. So we use CEPH Octopus. We have 2 storage servers, which 4 OSDs in total, and 1 NVMe drive each. Here to note maybe is that we have, with the 2 storage servers, the read throughput, we have around 6 gigabytes per server. So we should be able, if we have 1 client, to more or less drive the 100 gigabit line rate on the read throughput size, right? We configured CEPH without replication because we basically wanted to focus on not on the CEPH performance, more on the objective was how good does the gateway perform and the Bluefield, right? Right. So, and then we configured a few images to test against and left the object size to 4 megabytes. Okay, then let's look at the actual numbers. So we have starting with latency. What you see, these are typical latencies for CEPH, and these are QW1 16 kilobytes and 16 kilobytes because most of the cloud providers use 16 kilobytes to compare against each other. So normally in the storage environment, you'll see 4K, but it seems that cloud providers like to compare each other with 16K. So what you have from left to right is the baseline performance, the gateway, and the ARM running everything on the Bluefield ARM. And what you see here is that around 500 microseconds, a bit more, is the median latency in a typical libRBD baseline performance. So this is around 5 times higher than what the drive actually can do. Drive is around 90 microseconds, which is typical for CEPH. And then you see like 10%.
Hey, Jonas, we have
sure.
a couple of questions. Can we ask now?
Yeah, sure. Go ahead.
Okay. So the question is, has there been any research done using CentOS 8.x and containers?
On which side are we talking? Are we talking on the Bluefield or on the CEPH side?
Mike, you want to? Okay, Bluefield. Mm-hmm.
Okay, so for we have not this was basically what was officially available from NVIDIA at that point. They have their own kind of CentOS image that they provide to run it. We haven't tested with other Linux versions.
Okay. And then here's one more. What factors on the network were affecting the wide dispersion of read-write performance?
Read-write performance. For what performance are we talking about? So far, I've only shown, I think, maybe here, I think just the only slide that has read-write performance on there. But this is only drive performance. So this has nothing to do with the network, right? This is typically drive latency, write latency on the drives is lower because it's mostly cached. So this would not be sustained the 17 microseconds. I hope this answers the question.
It does, thank you.
Okay. And maybe here the difference between read and write is mostly because this is how CEPH works. So when you do a write, you also have metadata to write, and CEPH uses RocksDB to store metadata. And obviously, this also needs to be replicated to be fault tolerant. That is why the write latency here is double what you see on the read latency. And I think here what you see is that the overhead of running the gateway or running it on the ARM is I would say acceptable. It's maybe 10–20% higher depending on which you look at, right? So that would be a fine scenario to run. But let's look at more CPU intensive scenarios. And that's here, that would be a read IOPS at QDEP 128, also 16 kilobytes. And I left the write IOPS out. It looks very similar. But what you can see here, it's we have the IOPS here, and then on the we have different configurations. So we run 1 thread, 1 volume, 2 thread, 1 volume, and so on. I think they all show very similar pictures. So let's pick the one in the middle here. This is a 4 thread, 1 volume scenario. And again, from left to right, we have the baseline, the gateway, and the ARM performance. So on the very left, we have we have around 140K IOPS. Then we have the gateway, slightly lower, maybe 10% or so lower in performance. But then we have a huge drop down to 20K IOPS. And if you look at all the scenarios, it seems to be the maximum we can get out of running the CEPH client on the ARM side. And let's skip to the throughput. It looks very similar to the IOPS. Maybe first, when you look at the baseline performance, as I said before, since we have the 2 drives at 6 gigabytes each, we should be able to roughly get line speed performance. And you see we are somewhat close to it, not exactly, but there is some protocol overhead and other things into play. And CEPH setup is kind of small, but still you can see that we reach 10 gigabytes per second here. And the other thing I think is noticeable, the more threads you put in, the gateway seems to be scaling nicely. So if you have enough threads, you can almost get to a similar performance than what you see with the baseline performance. There's still a gap to the 10 gigabytes, but I would say it's still in an acceptable range. Whereas again, with the running everything on the ARM side, you get around 1 gigabyte per second here at the maximum out of it. And this was kind of what we've seen before, right? The TCP performance is already half. Now, if you add the additional overhead of the lib RBD on top of it, this is essentially where you end up with. Okay, what is the conclusion of all of this, right, of this proof of concept? So the embedded ARM on the current generation commodity SmartNICs is not fast enough to do complex data path operations at line speed, right? And so they should be mostly used for control, in my personal opinion. Officially, though, the SmartNICs vendors, like for instance NVIDIA, says this is a supported way of running this. So there's official documentation running DPDK or SPDK on the ARM side. So they expect their customer to run this, and you've seen the outcome, right? If you're fine with this performance, then okay, you can run the scenario like this. Then the second point I think you've seen is a gateway solution can be feasible, just at the cost of you need extra compute resources to do the translation between the protocols. And the other thing is fault tolerance is a bit more complicated because you need multipath NVMe over Fabric support, and your SmartNIC also needs to support it if you run it on the ASIC side. And the third thing is, okay, how can we, if we don't want to have a gateway, how can we make basically CEPH work on the SmartNIC? So the first one would be, okay, let's get a more programmable SmartNIC, like for instance, an FPGA solution. The downside is this is obvious that it's complex to program an FPGA. And the other thing is that these protocols like CEPH Rados protocol are always changing, right? So you always have to keep up with the changes if you want to deploy. If you update your backend, you need to also update your implementation of the client. So that's something you have to keep in mind doing this. Then the second part would be, okay, we could partially or fully offload the protocol. We could have an ASIC that supports Rados on the get-go. But then again, right, ASIC die space is very expensive. So which protocols do you pick? There are tons of storage protocols out there. And then you're only using one and the rest of the die is basically left unused. That's probably not something you want to have. And the last part is you could optimize librvd to be slimmer, right? Still, you would have the problem we've seen. TCP performance is not even there, so you probably also need some faster ARM cores. But then again, this comes down to what are the power requirements of that, and it's also a cost factor, right? In the end, and then maybe you are out of the sweet spot where you are more power efficient, and it costs less than deploying this in some other way. So that's essentially it. Thank you for listening, and I'm happy to talk to take your questions.
Any questions? All right. Thank you, Jonas. I appreciate your time, and I believe there were some questions early on. I don't see anything coming through the chat.
Okay. Thank you.